This presentation covers broader applications of geospace radars. This is a daunting task, and I will fall short of providing an objective and exhaustive overview of this topic. Time simply will not permit going through all of the possibilities. I hope that you'll forgive me if I fail to discuss something that may specifically be of interest to you. In the discussion that follows the presentations, there will be a chance for every voice to be heard. I would like to thank everyone who has provided valuable input to this talk, but all errors are purely mine. I have intentionally tried to avoid discussion of ionospheric observations, space weather, and radio astronomy, as other speakers have already covered these topics. So, what is a geospace radar? This term is used to describe a radar that has a powerful transmitter and an antenna with a large collecting area. These systems are used to study various physical phenomena in Earth's near space, in other words, geospace. Historically, the primary purpose of these radars has been to measure ionospheric plasma parameters using the incoherent scatter radar technique. The use of these powerful radars, however, hasn't been restricted to studies of the Earth's ionized upper atmosphere, as scientists have come up with many other applications. I'll give you an example of a powerful and large radar that had a wide range of broader applications. This is the Arecibo Observatory 305-meter dish, which was built with a primary goal of observing the scattering of electromagnetic waves from plasma, to allow us to study the Earth's ionized upper atmosphere. Before the construction even began, Kenneth Bowles showed that this goal could be achieved with another radar that was 100 times less sensitive than the Arecibo design. However, Arecibo went on to produce a wealth of information about the Earth's partly ionized upper atmosphere, for example, by making the most accurate measurements of ionospheric electron density ever made, and measuring the incoherent scatter spectrum so precisely that even just a few years ago, new advances in the theory of incoherent scatter could be made. It was a truly good thing that the radar was 100 times larger than it needed to be. The Arecibo system accomplished far more than that. For example, it produced scientific results that nobody had ever dreamed of when the system was first being planned. It found the first exoplanet. It made radar images of near-Earth asteroids and planetary bodies in our solar system. A Nobel Prize was awarded to Russell Hulse and James Taylor, who used Arecibo observations of a binary pulsar to confirm that energy is emitted in the form of gravitational waves. Arecibo was also used to search for signs of extraterrestrial intelligence, and it even sent a message to outer space. This is a topic that is controversial, especially in the scientific community, but yet it managed to capture the imagination of the general public. Up to its untimely end, Arecibo functioned as the most sensitive incoherent scatter radar, the most sensitive planetary radar, and one of the most sensitive astronomical radio telescopes in the world. I would say that Arecibo was a good example of a facility that had broader applications beyond its primary mission. What was the key to the success of Arecibo, especially when it comes to broader applications? Part of it must have been the enormous collecting area of the antenna, combined with frequency agility. In other words, the ability to radiate and receive radio waves across a wide range of frequencies with high directivity and high sensitivity. A large antenna area and frequency agility should still be at least part of the blueprint of a great discovery-class geospace radar of the future. I don't think we should settle for something the size of Arecibo. I think we should aim for something bigger. The large antenna area doesn't necessarily have to be achieved using a single big dish. The antenna doesn't have to be confined to a single location, and the transmitters that are part of a future system do not all need to be located in the same place as the receivers. The one capability that Arecibo didn't have was a multistatic observing geometry, the ability to observe a volume of space from multiple vantage points. Throughout this talk, I will point out why this could be beneficial in the future. The newest addition to the global network of geospace radars will be ISR 3D, which is to be located in northern Fennoscandia. The main novelty of this system is that it aims to measure the governing parameters of ionospheric plasma, including three-dimensional electric vector field. This is achieved using digital phased array technology and a tristatic observing geometry, which allows each measurement to produce a three-dimensional vector ion velocity, which can be related to three-dimensional electric field and neutral wind. The planned broader applications of ISR 3D include observations of meteoric matter in our solar system, the discovery of new near-Earth objects, the study of the composition and structure of the Moon, and monitoring the space debris environment. One goal specifically mentioned in the science case for ISCA 3D is the advancement of radar technology. The question that I've been tasked with answering in this presentation is, what can we accomplish in the future with a new radar system? I will cover 3 different application areas: studies of meteors, studies of the moon, and solar radar. These are examples of broader application areas where advances can be made using a new geospace radar facility. Powerful radars have been used to study meteoric matter entering the Earth's atmosphere ever since the Second World War, when major advances in radar technology were made. The scientific questions remain the same as they have throughout time. What is the influx of meteoric matter into Earth as a function of object size? Where does it originate from, and what does it consist of? What are the relevant physical processes involved with atmospheric entry? How does meteoric matter affect the Earth's climate, and what do meteors tell us about the evolution of our solar system? One question that continues to puzzle us is the lack of any widely accepted observations of meteors that have interstellar trajectories. In other words, meteors that originate from outside our own solar system. Why is this so? We have in recent years already seen 2 large interstellar objects with optical telescopes, Oumuamua and Comet Borisov, and yet there are no definitive observations of interstellar meteors. Perhaps the answer is that we simply don't have the right tools to make this measurement with sufficient accuracy. If we would be able to build a future radar system that could make accurate measurements of the interstellar population of meteors, we would obtain valuable information about the composition of interstellar space. One of the advantages of a powerful radar system is that it can observe meteors with masses measured in micrograms. These are not visible to the naked eye and are hard to observe using any other ground-based instrument. They are, however, easy to observe with powerful radars in the form of meteor head echoes, which are radar echoes from the cloud of ionization surrounding the ablating meteoroid. One major scientific challenge is accurately relating the radar cross-section of a meteor, which we can see with a radar, to the pre-atmospheric entry mass of the micrometeoroid. A path forward is to use state-of-the-art ablation models, combined with 3-dimensional models of plasma surrounding the meteor, and models of scattering from this plasma cloud. In order to obtain the most useful measurements, we would ideally want to observe the full trajectory of a meteor from atmospheric entry to the point where it is completely burned up in the atmosphere. This is something that current radar systems aren't able to do, except in very rare occasions when the meteor flies along the radar beam. An ideal radar system for observing meteor head echoes would be one that has the ability to monitor a large region of space simultaneously and quickly react to a newly observed meteor so that it can be followed throughout its full trajectory up to the point where ionization stops. What would be the optimal frequency from the signal-to-noise point of view, which would allow us to maximize the number of meteor head echoes? To first order, the radar cross-section of a meteor is a monotonically increasing function of the cross-sectional area of the plasma frequency contour where the electron density of the meteor head plasma matches the radar frequency. This means that the lower the frequency, the higher the signal-to-noise ratio. However, this doesn't mean that we should only use a low frequency. By measuring the same meteor with multiple frequencies, we would gain more information about the distribution of plasma surrounding the ablating meteor. In order to measure the trajectory of a meteor without ambiguity, the best method would be to use a multistatic geometry, where the trajectory is constrained by at least 3 different time-of-flight measurements between geographically separated receivers. This would avoid ambiguities that may arise with interferometry when the meteor is in the side lobes of the radar antenna. A multistatic geometry would also provide us with useful information about the 3-dimensional structure of the plasma surrounding the meteor. While most of the time we approximate the meteor head plasma as a spherical object, models show that it is expected to be somewhat elongated. Verifying models of meteor head plasma would require measurements of the same meteor not only with multiple frequencies which probe different distances from the meteoroid, but also from multiple look directions, allowing us to obtain information about the 3-dimensional distribution of meteor head plasma. With a sufficiently sensitive and agile radar system, it will be possible to observe several thousands of micrometeors per hour. If a long enough observing program is carried out, a truly remarkable catalog could be made, which would provide valuable input for future modeling efforts. Ideally, these radar measurements would be combined with a sensitive optical instrument that can provide complementary measurements of the meteors. This is a requirement that points to a site with good optical seeing conditions all year round. The Moon is our closest planetary companion, and it is easily within the reach of a geospace radar. Some key scientific questions are: what is the geological composition of the Moon? How was it formed, and how did it evolve? Using the inverse synthetic aperture radar technique, it is possible to make a polarimetric map of the visible side of the Moon using a powerful radar system. This is in fact something that has already been done since the late 50s. To this date, radar maps have been produced using several different wavelengths, including 7.5 meters, 6 meters, 70 centimeters, and 12.5 centimeters. These maps provide us with information about the surface composition and Bragg wavelength roughness down to approximately the skin depth of the radio wave. The longer the wavelength, the deeper below the subsurface the radio wave penetrates. The Earth's ionosphere, however, poses an increasing challenge to mapping the Moon with lower frequencies, causing perturbations to the signal that have the effect of blurring the radar measurement, which limits the resolution at which measurements can be made. Partly due to this reason, the lower frequencies are the ones that are least explored and are likely to provide us with new information. A future geospace radar that could be used to make low-frequency measurements would allow us to probe the subsurface to larger depths, allowing us to peer further back into the geological history of the Moon. We nowadays understand ionospheric propagation relatively well, and we already have techniques to correct for these effects by estimating the ionospheric phase delay to the signal. This is in fact something that has in the recent years already been applied to observations of the Moon and of Mars. It is quite probable that future low-frequency maps of the Moon would be of far better quality than those obtained in the 60s and 70s. What properties would a radar system ideally need to have in order to make advances in observations of the Moon? An ideal system should be able to make long observation arcs on a regular basis. Such a radar system would need to have a capability to transmit and receive electromagnetic waves with two orthogonal polarizations with a high polarization purity. For studies of structure and composition, this measurement would ideally be made across a range of different frequencies to cover different scales of roughness and surface penetration depths. It would be highly advantageous to have an interferometric receiver geometry to allow high-quality disambiguation of the Doppler north-south ambiguity. An optimal location for observing the Moon with a radar would be at a relatively low latitude, allowing for regular observations of the Moon at a high elevation angle. However, the location should also be one with a minimal presence of ionospheric irregularities, which would point to a location sufficiently far away from the geomagnetic equator. The first reported positive detection of a radar echo from the solar corona was in 1959 by Eshelman et al., using a relatively small 40 kilowatt radar system with a 25 dB antenna gain. This technique showed great promise, and a longer observing program was carried out by Jesse James in El Campo, Texas between 1961 and 1969. Several successful solar radar measurements were also made using Arecibo in 1966 and 1967 by Donald Campbell and Alan Parrish, but these remain unpublished. In the recent years, there have been multiple attempts to reproduce a solar radar experiment using the Hikamarka Radio Observatory 50 MHz radar, but these efforts have so far not been successful. Based on more than 16 failed attempts, it seems likely that many of the echoes observed with El Campo were not real. Based on the unsuccessful series of Hikamarka observations, it is estimated that solar radar echoes have to be at least a factor of 10 weaker than the earlier El Campo results would suggest. However, it was not possible to completely discount several effects that could result in a lower than expected radar cross-section. It was suggested that a new radar more powerful than Hikamarka or El Campo would be needed in order to make further progress. With a new geospace radar system which has sufficient frequency agility and transmit power, it would be possible to once and for all test the feasibility of making a radar measurement of the Sun using an Earth-based radar system. No matter the outcome, the rewards will be great. A negative result will tell us that there is something in the structure and composition of the solar corona that prevents a sufficient amount of radio waves to be scattered. This can potentially teach us something new about radio propagation in hot plasma. It could, for example, be complicated radio propagation in a highly irregular plasma structure, or it could be collisional losses. A positive result, on the other hand, can lead to a capability to routinely monitor the solar corona, giving us an early warning system for potentially hazardous coronal mass ejections, providing us with more time to shield our vital infrastructure in the case of a rare but potentially destructive space weather event. What would be the ideal properties for a radar system if it were to be used to observe the sun? The transmitter should be sufficiently powerful, and it should be able to transmit a continuous signal at full power for at least 16 minutes, which is the round-trip travel time between the Earth and the sun. The transmitter wouldn't need to have more directivity than the angular diameter of the solar disk. In other words, a beam width of approximately half a degree would be sufficient. If we look at the previous reports of solar radar measurements, we can see that we would need at least 100 kilowatts of transmit power to repeat the Arecibo results, and 500 kilowatts in order to repeat the El Campo results. The unsuccessful observations at Icamarca were already made with an average power of 150 kilowatts and a slightly larger antenna gain than the Arecibo or El Campo measurements, and yet these observations were not successful. This indicates that it would be a good idea to have a capacity to transmit at least a factor of 10 more power than what was used in the latest unsuccessful attempt. A geospace radar that observes echoes from the solar corona should have the ability of performing the measurement with a range of frequencies, much like an INOSOND, as different frequencies would be expected to be scattered at different distances from the sun. Previous solar radar measurements have been made with frequencies between 25 and 40 MHz. This would be a good starting point. Going much lower in frequency will result in problems with the radio wave getting out of the Earth's ionosphere, and a much higher frequency than 50 MHz will end up too deep in the solar atmosphere and likely be completely absorbed. The electromagnetic spectrum is unfortunately very crowded in this range of frequencies, making it important to have a high dynamic range receiver and a sufficiently high quality interferometer that would allow separating man-made radio interference and solar radio bursts from solar radar echoes. What would an ideal future geospace radar facility look like? What capabilities should it have? What would be the ideal location? These are questions to which there is no unique answer. Each application will have different needs. Lower frequencies have some interesting science, but this will exclude long-range planetary radar applications. A lower frequency will probably not allow plasma line measurements to be made, as superthermal enhancements of plasma lines are relatively small at longer wavelengths. A multistatic geometry would open up many new unexplored possibilities, but likely result in a system with less instantaneous signal-to-noise ratio than a single large system using the same amount of resources. If the transmitters for this future radar system are frequency agile, it would be possible to study the relatively unexplored frequency dimension of scattering models for various radar targets, including E-region plasma collisional models, ionospheric turbulence, meteor head plasma, and scattering from the lunar surface. If the frequency range of the system extends to low enough frequencies, the system could even be used for ionospheric modification. One opportunity that I see here is a collaboration with a radio astronomy instrument which would already provide the wideband receiving capability with a large collecting area and a high sensitivity. We would only need to add a capability for transmitting, and of course convince the astronomers to allow us to occasionally perform active experiments. Here is one example of a project where modern radio telescope hardware was used to study geospace, the Kilpisjärvi Atmospheric Imaging Receiver Array, which was nothing more than a LOFAR station built for the explicit purpose of studying various geospace phenomena. The system was primarily built to demonstrate the feasibility of conducting bistatic incoherent scatter radar measurements, together with the iSCAT VHF system. However, the applications go far beyond this. The Kaira system has been used as a receiver for Meteor radar and MST radar transmitters to study polar mesospheric summer echoes and meteor trails. It has been used for wide bandwidth studies of ionospheric scintillation by tracking bright radio stars. The same system has been used to study solar radio bursts, and it also acts as a wideband rheometer, monitoring cosmic radio noise absorption, allowing higher fidelity measurements to be made than would be possible with a single frequency imaging rheometer. Many of these experiments can in fact be done simultaneously due to the flexible hardware and software of the LOFAR radio telescope. My conclusion is that we should think big and be prepared for the unexpected. If we are to build a facility, We need to build one that is flexible enough to unite a critical mass of scientists and engineers to stand behind the project, but design it in such a way that everyone can follow their own paths towards their own research goals. It would be wise to design this instrument to be flexible enough to allow not only synoptic studies of ionospheric plasma, but to also allow it to be used for a broader range of applications, including studies of meteors, planetary radar, radio astronomy, and to leave room for radio science applications that haven't even been thought of yet. Thank you for listening.